today in this lecture we will discuss the spin coupling or spin splitting or the interaction between the spins. Every proton has two spin orientations. According to Boltzmann distribution pattern, protons with both the spins, that is plus half and minus half, we call it as this is alpha spin and this as the beta spin. Both the spin will be present in the sample. The interaction between the spins of the neighboring magnetic nuclei in a molecule. So consider like this. If this is one proton, this is another protons, and these protons will have two spins plus half and minus half. These protons also have two spins plus half and minus half. The interaction between the spins of neighboring magnetic nuclei in a molecule, if consider this one as a reference one, neighboring nuclei in a molecule may cause the splitting of NMR signal in the spectrum, and this is known as spin coupling, which occurs through bonds. 1, 2, 3, 3 bonds, which occurs through bonds and not in space, by means of a slight unpairing of bonding electrons. The spin of nearby nuclei affects the magnetic environment of the nucleus we are observing, and the signal for this is not a simple singlet but a multiplet. And the complexity, if this is the reference proton, the complexity of the multiplets depends upon the nature of the neighboring protons and the number of nearby protons or number of nearby hydrogen atoms. However, chemically equivalent protons do not show spin coupling due to interaction among themselves. Now we will consider how a doublet is obtained. We will consider protons here. This proton, this is A proton and this is B protons, and if this is the reference proton, this is the neighboring proton of this one, is one sigma bond, another sigma bond, and then 3 sigma bonds is separated by 3 sigma bonds, and this will have, this proton or this nuclei will have 2 spins. One is a plus half, and in another condition this will have a negative spin, minus half if this is the direction of the applied magnetic field HO. HO is the magnetic field applied in this direction, and the magnetic field of this Now we'll consider how a doublet is obtained in the NMR spectrum. This is the reference proton, and it has one neighboring protons, HA, and here also HA. This HA will have plus half spin, and this HA will have minus half spin, and this opposes the applied magnetic field, and this spin aligned with the applied magnetic field. Now every proton has two spins, plus half and minus half. We call it as alpha spin and beta spins. The magnetic field induced by these two spins of HA is transmitted to the adjacent proton HB through 3 sigma bonds. When a now first we will consider when a magnetic field of HA in alpha spin, that is, it is aligned with the applied magnetic field H naught, then HB will experience the applied field H naught and also the field induced by HA. So it experiences more of the applied field. At this stage, HB proton is more de-shielded than the proton without an adjacent proton and will undergo resonance slightly downfield. That means it requires less magnetic field for absorbance or for resonance because of the presence of an alpha spin of the adjacent proton HA. Now again, when we consider the other condition, when the magnetic field of HA is in beta spin, the HA protons is related to HB. It will now experience a field strength lesser than the applied field. We call it as shielded because the magnetic field of HA here, it is in a beta spin, opposes the applied magnetic field H naught. Therefore, this proton is shall to be shielded. Hence, we again HB protons will resonate at slightly upfield. Therefore, HB protons experience two magnetic fields. The net one is HO plus of HA, and another one is the applied magnetic field and minus of HA. So it will resonate 2 times or twice, and a signal will appear as a doublet. Since the population of the alpha spin as well as the beta spin is almost equal, 50% of alpha spin and 50% of the beta spin, the intensity of the doublet will almost same. Intensity of the doublet is almost same. See, if this is HA and HB, in the absence of HA, it has to appear a signal here, and here this is HO plus HA, and here this is HO minus HA. So this is the one signal and this is another signal. Now the HB appears as a doublet like this, and the intensity is 1:1. Intensity is 1:1. Now I will explain this in detail, and if this is the chemical shift of Hb if Ha protons were absent. Ha protons were absent. And now this is the signal this is chemical shift of Hb, chemical shift of Hb in 50% molecules shielded. Ha has spin opposed to applied field, and this is chemical shift of Hb in 50% molecules it is de-shielded proton Ha as spin aligned with the applied field. So this is the signal of chemical shift of Hb. Due to the chemical shift of Hb, if Ha protons were absent, if no Ha proton is absent, then this will appear as a singlet, appear as a single signet. And in presence of the neighboring proton Ha, it has two spins, one is plus half spin, another one is minus half spin, and here the chemical shift of Hb in 50% of the molecule is shielded, 50% of the molecule, and Ha has a spin opposed to the applied magnetic field. So we will get a signal here. This is due to HO minus of Ha. Now the another signal obtained is in the 50% of the molecule. Therefore here the chemical shift of Hb in 50% of the molecule, here it is de-shielded because the field, the protons of Ha protons will have alpha spin, its magnetic field is aligned with the applied magnetic field, so these proton will require less field strength. We call it as down field. The proton Ha has a spin aligned with the applied magnetic field. So in this way we will get, instead of one signal, we are getting two signals. Now similarly Ha protons, the neighboring proton is Hb protons will have two spins, one is plus half and another one is minus half. So this also influence or interacts with the neighboring proton Ha. Therefore, Ha proton also gives a doublet. So in this way, a doublet is obtained. Next, we'll see how a triplet is obtained. We'll consider the condition when this is Hb proton and here attached to two Ha protons. This is Ha and this is Ha dash. Two protons are attached to Hb and separated by 3 sigma bonds. This is one sigma bond, another one. 1, 2, 3. If this A is separated by or interact with this proton by 3 sigma bonds, 1, 2 and 3. And this is the direction of applied magnetic field. Now, Ha protons, Ha and Ha dash, Ha protons will have the following spin combination. The possibilities are, when the 3 possibilities are there. One is when both the spin will have on the same direction. Another one, both the spin will have beta spin, beta or opposite direction. And another one is up, another one is down. One is plus off, another one is minus off, and the other one is plus off and minus off. So three possibilities are there. Now this is Hb proton. First it interacts with Ha proton, then again it interacts with Ha dash proton. Ha dash protons, it overlaps. So doublet of a doublet, we call it as a triplet. And the intensity of the signal is like this. We are getting a triplet. Intensity is 1:2:1. The intensity of the signal here is 1:2:1. So in this way a triplet is obtained here. Now the Ha protons, they are magnetically equivalent. We cannot differentiate this proton with these protons. So both the protons will give a single peak, one peak, and these two protons is separated by 1, 2, 3 bonds by one neighboring proton, Hb. Therefore, these Ha protons will show a doublet. Ha protons will show a doublet and Hb protons will show a triplet. Now we will consider how a quartet is obtained. We will consider the case of C. This is Hb reference proton and it is attached to 3 protons. We mark it as Ha, Ha dash and Ha double dash. Now, the different possibilities of the spin states are when all these protons are equivalent in all respect. Here there are 4 possibilities are there. The first one, all the 3 protons will have alpha spin, and another one is all the 3 protons will have beta spins, and next 2 protons will have alpha and 1 beta, and 2 protons I will have beta spin and 1 alpha, and another one only 3. So here there are 4 possibilities are there, 4 possibilities, and here if this is HB interacts with the HA protons, again it interacts with the HB proton, again it interacts with the here HA dash and HA double dash. So here we will get 1, 2, 3, 4 signals. 4 signals are there. The intensity of the signal is 1:3:3, 1:3:3:1. 4 signals are there. They appears as like this. Four signals appears like this. Now the magnetic field felt by all these protons with the HB protons. Here all these protons are equivalent in all respect. So they interact with the B protons. 1, 2, 3 sigma bonds, 1, 2, 3 sigma bonds, 1, 2, 3 sigma bonds. So HA protons have only one neighboring protons. HA dash will have only one neighboring protons. HA double dash also having one neighboring protons. So HA will exist as a doublet. HA will exist as a doublet and HB will exist at a quartet. The 3 protons are there. So in this way the splitting of signals will take place, and this depends upon the number of protons or magnetic nuclei in the neighboring carbon atoms. And now next we will consider the term coupling constant. Coupling constant. The distance between the spacing of the adjacent lines, in the multiplex is a direct measure of spin-spin coupling of protons and is known as coupling constant, where the term used for that is J. Coupling constant J. The value of J is independent of the external field and it is expressed in Hertz. Its value is usually ranges from 0 to 18 Hertz. So this is the meaning of coupling constants and spin-spin splittings. Next we will consider the rules. Rules for splitting pattern. Rules for splitting pattern. There are 4 rules are there. The first one is a proton that has n equivalent neighboring protons. A proton, if this is a reference proton, if this proton has n number of equivalent neighboring protons, then this proton will split up into 2ni plus 1 peaks. 2ni plus 1 peaks, where I is the spin, that is equal to half. So 2 into n into half plus 1. That is, this 2 and 2 cancels. We will get n plus 1. N plus 1. We call it as n plus 1 rule, or n plus 1 with the coupling constant J. That means if the proton has, if n is the number of neighboring protons, then this proton will splits up into n plus 1 peaks. N plus 1. If one adjacent proton is there, then it is 1 plus 1 is equal to 2. We'll take an example of CH3, CH2, Cl. For this proton, here n plus 1. N plus 1. N is the number of neighboring protons. Here 2 neighboring protons are there. So therefore 2 neighboring protons plus 1, that is equal to 3. So this exists as a triplet. This one as a triplet. Now for this n plus 1, the n is the number of neighboring proton. Here the neighboring carbon atom has 3 protons. So n is equal to 3 plus 1 is equal to 4. So this exists as a quartet. This exists as a quartet. The second rule is chemically equivalent protons. Chemically equivalent protons do not exhibit splitting. Do not exhibit splitting. The equivalent protons may be on the same carbon atom, or it may be on the adjacent carbon atom, on the other carbon atoms. So we'll take an example here: C, Cl and H and H and H. Here this proton is attached to this carbon atom. This proton, 3 protons are there. All protons are equivalent in all respects. All protons are equivalent in all respects. We will get only one signal. No splitting is possible here. No splitting takes place here. Now here C, this is another example. This is another example. Here 1, 2, 3, 4 protons are there. All these 4 protons are chemically equivalent in all respects. We cannot differentiate this proton with this one, with this one or this one, because all protons, here it is 1, 2, 3 separated by 3 bonds, 1, 2, 3 separated by 3 bonds. Even though it is separated by 3 bonds, even though the adjacent protons are there, but we cannot differentiate these protons. All protons are equivalent, chemically equivalent. So they will not interact with each other. The spins will not interact with each other, and we will get only one signal. No coupling. No coupling, and we will get a singlet. Next, number 3. Rules number 3 is protons that are farther than 2 carbon atoms. Protons, they are farther than 2 carbon atoms. So that means here 1, 2, 3 bonds are there. So protons are attached to the adjacent carbon atom. Here coupling is there. The protons will be coupled. But here if the protons H, C and here H, 1, 2, 3, 4 bonds. 4 bonds are there. In this case, this proton is separated more than one carbon atoms or 4 bonds, here no coupling. Coupling will not take place and are ordinary conditions. So they show a small coupling when they are separated by pi bonds. When they are separated by pi bonds, they show a small coupling. The next rule, fourth rule says that two groups of protons coupled with each other, they must have same coupling constant. Same coupling constant. Two groups, they coupled with each other. Two groups, they coupled with each other, they will have a same coupling constant. So these are the rules. I will summarize one. The first one is the rule is one n+1 rule. If the number of adjacent carbon atom is n, then the multiplicity is n+1. n+1. If one adjacent carbon atom is there, then we will get a doublet. If two adjacent carbon atom is there, we will get a doublet, a triplet. If three, we will get a quartet, n+1. And chemically equivalent protons, second one, they do not couple with each other. They will not exhibit splitting. No coupling takes place in the case of chemically equivalent among chemically equivalent protons. And the protons attached to more than 3 bonds, 1, 2, they are separated by more than 3 bonds, then they usually do not undergo coupling. And the groups or protons, they coupled with each other. Two groups of protons coupled with each other, they must have same same coupling constants. They must have same coupling constant. Next we'll discuss the meaning of Pascal triangle. Pascal triangle. Pascal triangle showing the relative intensities of peaks of multiplets arising from coupling with the equivalent protons. Again with the equivalent protons. So we will see how Pascal triangle appears. This is the number of adjacent protons and type of multiplicity and ratio of intensities. Now, if the adjacent proton is 0, no adjacent proton, we will get a singlet. This is marked as S, represents a singlet, and we will get only one signal, and the intensity is 100%. Intensity is 100%. If there are one adjacent carbon atom, one adjacent proton separated by 3 bonds, one hydrogen atom, adjacent hydrogen atom, then it will get n+1. This is number n. n+1 is, we get a doublet and is denoted by small letter d, and the ratio of the intensity is 1:1. And if the number of proton is 3, adjacent proton is 3, we will get a triplet designated as this one. So we can write is 1:2:1. And if the adjacent proton, it is 2, adjacent proton is 2, then n plus, adjacent proton is 2, n plus 1 is triplet. If the adjacent proton is 3, then n plus 1, it is quartets. Q will get 1:3:3:1. And if the adjacent protons number of n is equal to 4, then we will get a quintet. And its intensity is 1:4:6:4:1. 1, 2, 3, 4, 5. And if the number of adjacent proton is 5, then we will get a sextet. The intensity is 1:5:10:5:1. 1, 2, 3, 4, 5, 6. A sextet. And then if the number of adjacent proton is 6, n is equal to 6, we will get a septet. A septet, its intensity is 1:6:15:20:15:6:1. And this appears as a triangle like this. This triangle is known as Pascal triangle. It is showing the relative intensities of peaks of multiplets arising from coupling with the equivalent protons. So this triangle is known as a Pascal triangle. Now we'll discuss some examples. If this is H, no protons, no adjacent protons, we will get a singlet. And if this is the reference proton HB, and one HA proton, then we will get a doublet. And if like this, if two protons are there, for this one adjacent proton is there, and HA will exist as a doublet, and HB, this is HA, and HB, there are two neighboring protons, two adjacent protons separated by 3 bonds. It exists as a triplet. This is HB, 2 is there, it is a triplet. Now we'll take an example, another one. This is HB and there are 3 protons, and HA, only one adjacent proton, 1, 2, 3 bonds, 1, 2, 3 bonds. So HA proton will have a doublet, and HB, there are 3 protons are there, 1, 2, 3. So it 3 plus 1, n plus 1 is a quartet. We will get a quartet with intensity, this is HB, 1:3 3:1. This is the intensity of the peaks. So in this case here HB protons, HA protons and HB protons. HB protons, there are 3 neighboring protons are there. We will have a doublet. HA protons, only one neighboring proton is there. So HA signal will appear as a doublet, and HB there are 3 neighboring protons. So 3 plus 1 is a quartet. So here we will get a quartet. Now we will consider Cl, CH2, Cl. Here both the protons are equivalent in all respects. Here 2 protons and here 2 protons. There are 4 protons are there, and both set of protons. All the 4 protons are equivalent in all respect. So no coupling with each other. Chemically equivalent protons, they do not couple with each other. So it gives only one peak, a singlet. A singlet will get. And if is Cl, another one is CH2, and this is CH2, and here Br. So here this carbon atom is attached to 2 hydrogen atom and 1 chlorine atom. This carbon atom is attached to 2 hydrogen atom and bromine atom. Now these 2 protons are not chemically equivalent. They are not chemically equivalent. So their chemical environment is changed. So this will give one type of signal. This gives another type of signal. So we will get a 2 doublet. We will get a 2 doublet in this case. We will take another example. So here this is HA proton or HB proton, and all this is HA, and this is also HA. This proton is surrounded by how many? 1, 2, 3, 4, 5, 6 protons, and all these protons are equivalent. But for this HB protons, there are 6 neighboring protons. So HB proton will exist as a septet. 1, 2, 3, 4, 5 and 6 will get septet. Like this. This is HB and HA protons. All these protons, they are chemically equivalent. Chemically equivalent protons, they do not usually interact with each other. So therefore only one adjacent proton is there. So all these 6 protons will give a doublet. They will give a doublet. So this is HA protons, a doublet. So in this way the splitting or spin splitting in NMR takes place. This is the brief discussion on the spin splitting in NMR spectroscopy. Thank you.